Thank you for this opportunity to present a brief introduction to the benefits of using social robots in education. I will also highlight some recent warning signs of potential problems that may be encountered. During the last decade, there has been a dramatic increase in both research on and general interest in how social robots can be used in classrooms. The number of publications have more than tripled, and major news media have reported on how robots, not the least Furhat, can be used in education. This increased interest corresponds time-wise to the founding and growth of Furhat Robotics. I'm not claiming any causality here in general, but the birth of Furhat definitely influenced my own research focus when I shifted from screen-based computer-animated teachers to social robots. The first question that we as researchers in social educational robotics are often asked is why robots should be used in education. First of all, it should be emphasized that there is no intention of replacing teachers, but to complement them by offering additional practice for their students. Secondly, it is sometimes asked if it would not be as good to use a screen-based agent that is much less expensive and less complicated. But a master thesis from 2015 that I supervised confirmed what the other researchers had already proposed. Students learn better with robots than with screen-based agents or with an impersonal interface. And this is mainly because they find it more stimulating to interact with a robot. We may also need to consider what constitutes a social educational robot. There has in fact been quite a variety of definitions. Some commonly used criteria include that it should have a physical 3D embodiment, that it should interact with humans in a formal educational setting, taking on an educational role with some autonomy. Additional criteria that have been proposed are that the robot should have some biomorphic features and some knowledge of social norms. Let us illustrate and to some extent modify this categorical view by considering the use case of language learning. What makes a specific robot suitable for an educational task depends on the robot's educational role, the pedagogical strategies that are being used, and the learner's age. Simply put, while toy-like robots may feel more familiar and less frightening to smaller children to play with as a peer, robots that are more human-like in appearance and interaction are often more appropriate for older learners, in particular if the robot should convey some expertise, such as in a tutoring role. I will now focus on two specific use cases that exemplify how robots can be used in language practice and in STEM problem solving. These two cases illustrate some of the benefits, but also potential problems of using social robots in education. For the multi-party robot-assisted language practice, we initially focused on how the robot should interact as a conversational partner to encourage learners to speak as much as possible, and found that differences in the robot's interaction style clearly influenced the learners' speaking activity and their perception of the robot. But I'm rather going to focus on a particular aspect of how robots can be used to encourage learner participation through gaze behavior and directed feedback signals. And this is because these are features that illustrate the benefits of using a robot compared to a screen-based avatar. In a language practice setting, it is common that one participant speaks much more than the other, due to differences in personality or in proficiency. We have explored how the robot could encourage the more silent participant through subtle gaze and vocal feedback signals. The main findings in these studies, indicated by the red arrows, were in the first study in which the robot used gaze, that this could make the balance in the share of the interaction more even between the high and low proficient speakers. And in the second, in which the robot used vocal feedback, like directed to the more silent speaker to encourage that speaker to speak more, that this could encourage lower proficiency speakers to speak more. And note that these signals are implicit and intuitive, hence illustrating the benefits of using a human-like robot. The next use case focuses on using robots in STEM education, with some take-home messages about students' critical thinking in interactions with AI. And this is relevant now that social robots are more and more frequently being driven by large language models that may present factual incorrectness, not the least in STEM subjects. We have performed 2 studies, one with the 3-tiered math problem, in which the robot was correct and supported the student in the first 2 parts of the problem, and then proposed an incorrect solution in the last. In the second, the robot and the student collectively answered 8 true-false statements about electric circuits, with the robot arguing for the incorrect answer on 2 of the questions. For the math problem, we conducted an exploratory study with high school students from one same class who had recently worked on similar geometric problems and were well familiar with the theorems to apply. We analyzed the interaction before and after the descent when the robot proposed an incorrect solution. Of the 22 students, 3 immediately accepted the robot's incorrect solution. An additional 11 were persuaded by the robot's incorrect arguments, while 8 resisted and maintained their own correct solution. So almost 2/3 of the students were misled by the robot. Moreover, we found that the outcome of the descent could actually be predicted by the students' answers on the pretest questionnaire and their interaction before the descent. Students who self-assessed as being good at math were more prone to resist persuasion. But students who had a more positive attitude towards robots were persuaded to a larger extent. And in line with other recent studies, we also found that more frequent use of GPT led students to being less critical towards the robot's claim. On the other hand, students who had actually interacted more with robots were less persuadable. We also see in the bottom left graph that a student's gaze at a task paper could predict if they were going to be persuaded. In the experiment with the electric circuits, the students first gave a preliminary answer, then discussed with the robot and gave a final answer. We found that 75% of the 40 high school students performed beyond expectations based on a preceding diagnostic test. The green arrows indicate a significant improvement in answer correctness for all questions on which the robot argued for the correct solution, and the red a significant decline on the 2 questions on which the robot was wrong. So, since we have this problem of students following the robot's advice, regardless of if it's correct or not, we have started exploring how the robot itself could promote students' critical thinking by indicating how certain it is regarding its claims. In the electric circuits test, the robot expressed certainty or uncertainty on 4 of the questions using verbal, prosodic, and facial signals. Let's look at 2 examples. The first is of a certain robot.
Okay. I'm positive. It's true. So do you agree?
For the example of the uncertain robot, I have removed the audio since it makes it easier to focus on only the facial signals. We found a significant difference in the students' alignment rate depending on if the robot displayed certainty or uncertainty. In this experiment, the robot had a correct answer when it was being certain or uncertain. In a new study that we are currently preparing, we will investigate the effects of robot certainty when it has the incorrect answer as well. And to tie back to the question of how robots differ from screen-based agents, we will assess if a screen-based virtual robot is as persuasive as a physical. For this study, we are merging our 2 use cases, focusing on a second language practice game inspired by the Connections game. With this hopefully positive outlook to future use of social robots in education, I would like to end my presentation by thanking you for listening and my current and previous collaborators in these studies.